Hello, my name is Sahil Kumar, roll number 2201 CS60, and today I'll be walking you through my implementation of assignment 11, which focus on secure multi-party computation, especially the sum protocol. The goal of this assignment is to allow in participant to compute the sum of their private input without even revealing their individual secret to each other. We use an additive secret sharing mechanism to make this happen. Let's dive right into the code. So here we have a class SMPC protocol. In the init constructor we pass our participant dynamically. Notice my variable names include my name and roll number, like Sahil 2201 CS60 as specified in our assignment requirement. Here it is. We initialize the number of participants, and critically we set our module to the 2 to the power 32. The 32 bits module secure that all our modular arithmetic loops around effectively hiding the actual raw numbers. This is the self modules. This is the module 2 to the power 32. Now next up is the share secret function. This is how a participant divides their private inputs into the shares. For every other participant, we generate a random number using the rand init 1 to 100 here, and these random numbers are distributed as the shares, but to ensure the summation remains accurate, that participants calculate their own share by subtracting the sum of all those random numbers from their true secrets. Finally, they apply the modulo 2 to the power 32 to that result. That dictionary of share is what we get distributed. Once everyone has received share from everyone else, they run compute partial sum. This no one know anyone else's secret. They only have meaningless random shares, but each person's sum up everything they receive, apply the modulo and compute a partial sum. Finally, we have reconstruct the result. It takes all the participant partial sum and add them together under the same modulus and output the final result. Instead of using the hard-coded inputs, I have designed a main function to dynamically accept the number of participants, their names, and their secrets interactively. Let's run this code in terminals and see it in the actions. Python SMPC Sahil 2201 CS60.py. Here it is asking number of participants. The number of participants is 4. First participant name is Alice, and the private input for Alice is 40, and the second participant name is Bob, and private input for Bob is 17. Then third participant name is Charlie, private input is 100, and the fourth one is David, and the private input is 255. Now Here this is the looking at the printed log. The expected sum is 412. Let's see how our protocol gets there securely. For the phase 1, you can see Alice gets her cigarettes 40 and generate completely random shares for Bob, Charlie, and Davids, and calculate her own share, which results in a massive number due to a model wrapping on a wrap round on the negative numbers. There you can see the for the phase 1 share for Bob is 86 and Charlie for 88 and for David it is for 48. Now for the this is for a phase 2, and these shares are distributed over the now for the phase 2 these shares are distributed over the network to the respective peers. For the phase 3, each participants aggregate their receipt number to create their partial sum. Notice how Bob's partial sum look like a random huge number. This is the huge number. That means nothing on its own. Now for the phase 4, in the result reconstruction phase, we grab everyone partial sum 50. Like what was the everyone partial sum? This one, and we add them all up and take the modulo 2 to the power 32. So we get 412. So the computed sum is 412 and the expected sum is also 412. So and that proof our secure multi-party computations allow us to calculate accurate results over the network without sacrificing privacy. This concludes my explanation of this assignment. Thank you for watching.